Hello all, let's start chapter 4, the first section of chapter 4, 4.1, exponential functions. Which kind of functions? We call them exponential. We will start from here, then we learn how to graph exponential functions, and slowly in 4.2, I'll teach you a new topic, which we call it logarithms. But before discussing logarithms, let's first learn what is exponential functions. Any function that's written in the form of f of x equals b to the power of x, we call it exponential function. Here, your b cannot be 1. Your b also cannot be less than 0. Correct? It means your b is always greater than 0, but not also 1. B, we call b base, and x is your exponent. Correct? Numeric example, f of x equals 2 to the power of x. This function, I call it exponential. Remember one thing, in exponential functions, your variable is always exponent. Your base is always a number. Or another example, f of x equals 1/2 to the power of x plus 1. You see again, x is in the exponent. I call this function an exponential function. There are two types of exponential function. The first type, f of x equals b to the power of x, but in this form, your b is always greater than 1. Correct? We call this type of exponential function an increasing exponential function, or some professors in some books, they gave a special name to this function. We call it exponential growth. Correct? When your base is always greater than what? Greater than 1. For example, f of x equals 3 to the power of x. You see, 3 is greater than 1. Or g of x equals 5 to the power of x. Or x plus 1. Correct? We call this type of exponential functions increasing exponential functions or exponential growth. Later, when I start graphing, I will show you why we call it increasing. The second type of the exponential functions, still we write the same notation, f of x equals b to the power of x, but here your b is greater than 0, but less than what? Less than 1. It means all fractions between 0 and 1, if your base is one of those fractions, we call it a decreasing function, or the actual name is exponential decay. For example, f of x equals 1/2 to the power of what? X. Or f of x equals 3/4 to the power of what? X. We call these types the decreasing exponential function. Now, let's start graphing exponential functions. I will explain graphing in examples for you. Example number 1. Graph f of x equals 2 to the power of x. Usually, when you want to graph an exponential function, use a table of values and use always 5 points, correct? Minimum 5 points. Here, x and y, or x and f of x, correct? And I will use 5 points to graph my function. 0, 1, 2, and 2 negative numbers may be here, -1 and -2. Correct? Let's plug in these values. In this example, I'll plug all the values for you and I'll show it to you how to calculate. First, I want to find f of 2. F of 2 equals 2 to the power of 2, which gives me what? 4. Next, f of 1, it means 2 to the power of 1, which gives me what? 2. Next one, f of 0, which means 2 to the power of 0. Any number to the power of 0 is 1, correct? 1. Now, f of -1, it means 2 to the power of -1. Please remember, you cannot raise a number to a negative exponent. Do you remember from intermediate algebra that if you have x to the power of -n, you can write this as a 1 over x to the power of +n. Then 2 to the power of -1 equals 1 over 2 to the power of +1, which gives you what? 1/2. Same way, f of -2 equals 2 to the power of -2. It means 1 over 2 to the power of +2, which gives you what? 1/4. Now, using this table, easily I can graph my function. Correct? Let's graph it now. Here x, here y, 1, 2, 3, 4, 5, -1, -2, -3, -4, 1, 2, 3, 1, -1, -2, -3, here 0. When x is 2, y is 4. x2, y4, somewhere here. When x is 1, y is 2. x1, y2, this point. When x is 0, y is 1, which is this point, the y-intercept, correct? When x is -1, y is half. -1 and half will be here. When x is -2, y is 1/4, which is this point. Now, if I connect all these points, that will be the shape of the graph of f of x equals 2 to the power of x. You see, because your b is greater than 1 here, your graph is increasing. Or in your book, it's explained that the graph rises from the left to the right. Correct? And we call this type of function exponential growth or an increasing function. Correct? Let me do another example for you. F of x equals 1/2 to the power of x. Again, we want to graph this function. I'll use a table of xy and 5 points. 0, 1, 2, -1, -2. If I plug in 2, if I look for the f of 2 equals 1/2 to the power of 2. And you know, when you raise a fraction to a power, you have to raise the numerator and denominator to that power. 1 square is 1, 2 square is what? 4. It means y becomes 1/4. F of 1 equals 1/2 to the power of 1, which gives you 1/2. F of 0 will be 1/2 to the power of 0, which gives you what? 1. F of -1 gives you 1/2 to the power of -1. It means, remember when your professor explained when you were in intermediate algebra, if you have a over b to the power of -m, the easy way to change this exponent to positive, you can do b over a to the power of what? Positive m. It means here I can write 2 over 1 to the power of 1, which gives me 2. F of -2 equals 1/2 to the power of -2. Again, it will be 2 over 1 to the power of 2, which gives me what? 4. Now I have the table. Easily, I can graph this function. xy. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. -1, -2, -3, -4, -5. When x is 2, y is 1/4. x2 1/4, it means if this is 1, 1/4 of that, which is really close to x. When x is 1, y is half. 1 and half will be a little bit over this point. 0 and 1, of course, this point. -1 and 2 will be this point, and -2 and 4 will be this point. And if I connect these points, remember your graph never touches the x-axis, or you can call the x-axis the horizontal asymptote for these functions. In this example, you see that your b is equal 1/2, which is greater than 0, less than 1. That's why the graph falls from left to right, or we call it an exponential decay. Correct? Now, after doing these two examples, now I will talk a little bit, because you saw it on the graphs, about the characteristics of the exponential functions. Correct? First, number 1. What are the characteristics of the exponential functions? Number 1, domain of the exponential functions. In both examples, in both graphs, you see that your domain starts from -infinity to +infinity. Then characteristic number 1 for the exponential functions, their domain is always from -infinity to +infinity. Or in other language, the domain of exponential functions are all real numbers. Number 2, range. As you see in both graphs, the range of exponential functions is always 0 to infinity. When I'm saying 0 to infinity, it means I will never cross the x-axis, but I'll come really, really, really close to the x-axis, but I cannot intersect the x-axis. Correct? Number 3. If you have f of x equals b to the power of x and your b is greater than 0, your graph is always increasing. Increasing means it's increasing from the left to the right. Correct? Number 4. If you have f of x equals b to the power of x and your b is less than 1 greater than 0, in this case your function is decreasing. It means your function falls from the left to the right. Number 5. The graph of the exponential function always passes from this point. It's a good characteristic. You see, in both graphs, you see the graph is passing from point 0, 1, or it means the y-intercept for the exponential function is always 0 and 1. It's an interesting characteristic of the exponential functions. Your y-intercept is always what? 0 and 1. Number 6. Easily you can see that f of x equals b to the power of x is a one-to-one function. Because the graph was like this way, or the graph was like this, right? XY. And if you do a horizontal line test, if you remember what is one-to-one function, which I explained it in last chapter, you see your horizontal line always crosses the graph at one point. Then it's a one-to-one function. Okay, if f of x equal b to the power of x is a one-to-one function, it means exponential functions then have an inverse function too. Correct? Later in 4.2, I will discuss what is the inverse of an exponential function. Actually, the inverse of an exponential function will be the logarithmic function. Correct? If I put one more characteristic, when you have f of x equal b to the power of x, your graph is approaching to the x-axis really, really close, but never intersect the x-axis, which we call the x-axis the horizontal asymptote. These are the main characteristics of an exponential function. Correct? One more thing that you have to remember, your b, in both cases, I told you, b should be greater than 1 or b can be greater than 0, less than 1. If someone gives me this function f of x equals negative 1 to the power of x, and they ask me, is this an exponential function? My answer immediately will be no. because negative 1 is b, and your b cannot be less than 0. It means, in a simple language, in an exponential function, the base cannot be negative numbers. Correct? Your base is always positive numbers, not negative numbers. Now, when we learned easily how to graph an exponential function, of course, now we can talk about transformation of exponential functions, correct? Hopefully you remember what's transformation. Transformation of exponential functions. I will give you just here the cases. I will maybe graph one of them for you because we already discussed what is transformation and here or translation. Here I'll just show it for you in a table, correct? The first one, if you have f of x equals b to the power of x, here plus c, or if you have f of x equals b to the power of x minus c, here if you have plus c, your exponential function shifts c unit up, and if you have minus c, your exponential function shifts c units down. Correct? If I show you in a graph, two graphs, the transformation, for example, if this is the graph of f of x equals b to the power of x, if you have this graph, will be the graph of f of x equals b to the power of x minus c. You are shifting c units down, or you can shift your graph c units up. How to deal with the table? We already discussed in the chapter that I talk about transformation. You use your table, and what you do, add c to the y column, whatever that c is, 2, 3, whatever that number is given, or subtract that number from your y column, and it gives you the transformation. Correct? Next, if you have f of x equals b to the power of x plus c, or if you have f of x equal b to the power of x minus c. If you have x plus c, your graph shifts c unit to the left, and you have x minus c, your graph shifts c unit to the right. Next one is reflection, right? All the transformation, the table that we discussed in transformation. If I have f of x equals vertical stretch. If you have f of x equals b to the power of, cb to the power of x, correct? In this case, you have a vertical stretch or shrink based on what is this number c. And last one, if you have f of x equal b to the power of cx, you have a horizontal stretch or shrink. I will do just one example for you here to show maybe a vertical shift or horizontal shift. The rest is the same. Why I'm not doing a lot of examples? Because at the beginning of the semester that I told you, when we explain something in one chapter, you will see it comes in your book again and again and again. We already learned how to do transformation or translation of a graph. We just apply that rule here when we talk about exponential functions. When you talk about quadratic, of course, you apply your rule on quadratic functions, correct? When we talk later about logarithmic, you can apply the rule on logarithmic functions, correct? But anyway, I'll do at least one example here for you to show how I'm using transformation or translation to graph an exponential function. For example, graph f of x equals, let's say, 3 to the power of x plus 1. What you do, if you remember, you first graph this one, f of x equals 3 to the power of x. Then later, you work on your shift. What I do, I'll draw a table here, x and y, use 5 points, 1, 2, -1, -2, and I will graph first f of x equals 3 to the power of x. When x is 2, y becomes 9. When x is 1, y becomes 3. When x is 0, y becomes 1. When x is -1, y becomes 1/3. When x is -2, y becomes 1/9. I didn't show the work because I show it in example number 1 and 2. Correct? Now, what I do, first I'll graph my parent or base graph. Correct? 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. When x is 2, y is 9. When x 2, y 9, this point. When x is 1, y is 3. Of course, this point. x 0, y 1, your y-intercept characteristic, -1 and 1/3, which will be somewhere here, -2 and 1/9, which is really, really close to the x-axis. And you can, let me change the color, just connect these points, and this one will be the graph of f of x equals 3 to the power of x. But that's not my concern. My concern is to graph 3 to the power of x plus 1. Your 1 is c, right? It means you will add 1 to the column of y, and that gives you a vertical shift. Or in the graph, just move all the points 1 unit up. Correct? It gives you your vertical shift. 9 plus 1 is 10. 3 plus 1 is 4. 1 plus 1 gives you 2. 1/3 plus 1 gives you 4/3, or 1/1/3, correct? And this one gives you 1/1/9. These are the new y's use the old x and the new y, and easily you can find the graph, correct? If I use the green color, when x is 2, y is 10, somewhere here. When x is 1, y is 4. 1 and 4 will be here. 0 and 2 will be here. Same way, negative 1 and 1/3, or 1 and 1/3, which is somewhere here, and next one will be here. Everything shift one unit up. The graph goes actually like this. My graph is not good because I'm just using an electric pen, but if you use a graph paper, easily you can graph it really nice, correct? This was all about part of section 4.1. I'll stop the lecture here because I just start with the base information about exponential functions. In part 2 of this video, I'll discuss with you what is natural number e. We will discuss what is e. That you will see after this a lot we are using number e. And also I'll do some word problems on a very interesting topic that we call it compound interest. Correct? It's a banking problem, it's the money problem. We will discuss compound interest formula because the compound interest formula is actually an exponential function. Correct? I'll stop the lecture here and see you in part 2 of this lecture.